All right. Welcome to card number 8. Um, this is parallel circuits, and this is an important card because it combines what we covered in an earlier card on parallel resistance with parallel voltage now, and you need to know how they work together. And the reason for that is this: it's, all vehicle circuits are parallel. And another part of this that's important is that in vehicles and systems that we work on, there's only one load per circuit. Okay, um, I know people want to believe that the vehicle has a headlight circuit, but it isn't. It's headlight circuits. And if you're in school learning this, um, it's important to understand, and you don't want to be disrespectful to your instructor, but the way it's been taught forever and ever and ever is to say that this would be a circuit. Okay, this is not a circuit. This is 5 separate circuits, because there's a path for electrons through this one, then there's a path here, there's a path here, path here, and a path here. And if I were to cut any of these out, for example, this is a 1 million or 1 mega ohm. If I were to cut this one out, it would turn off, but the other 4 would stay on. Yes, they share a fuse. All 5 of them share a fuse in the circuit, and kind of they all share a ground. Not really, but kind of. And my biggest concern is that this math is more difficult. And because this math is more difficult, it doesn't get taught as aggressively or as effectively as it could be. But the reality is the math is not that tough if you use this 1 over x button on the calculator. Okay, so the way that I suggest you do it is, if, in the last card we had 100 ohms plus 50 ohms plus 10 ohms, and all that equaled 160 ohms. All right, well, that's in series. Okay, and that's series means one after the other. All right, well, in parallel, it's not quite the same. Oh, parallel. There's an L that comes there. Okay, parallel. 2 L's actually. Parallel. In parallel, it would be 100 ohms 1 over x plus 50 ohms 1 over x. Let me put this in here so I can kind of show you. Here's the 1 over x button right there. And what it does is it flips things over, and I'll explain that in a second. Plus 10 ohms 1 over x equals some number, and then you flip that back over again. Okay. What does the 1 over x button do? All right, well, and by the way, yes, that's blood. I cut the crap out of my thumb. See that? Cut the crap out of my thumb. Right. What the 1 over x button does is it takes any number and flips it over. All right, so let's just take the number 37. Okay, and I like 3s and 7s. I don't know why. Okay, well, the number 37 can be written as a fraction, because 37 over 1 is a fraction. And what this fraction is asking is how many 1s fit into 37, and the answer is 37. Okay, well, if I hit the 1 over x button, then that's going to become 1 over 37. Well, how many times does 37 go into 1? Well, only part of it does, and the answer is 1/37th of it. So this question is asking, what is 1/37th of something? So 37 would go into 1. No. 37 goes into 10. No. 37 goes into 100. Yeah, not quite 3 times. So it's going to be about 0.02. So it's going to be 0.02. I just made this up, so I'm probably going to get it wrong, probably. 37 would go into 100 2 times. That would leave 60. 74 would leave 26. It's about a third. I'm going to say about 2.4. All right, so let's see what it does. I'm making this up. But what I'm doing is I'm just saying, how many times would 37 go into 1? No. 10? No. 100? Yeah. 37 goes into 100, and because of the extra zeros here, we just add decimal points. So I'm going to get this wrong. I know I'm going to get it wrong. Yeah, it's 0.027. Okay. But I was close. So it's actually 0.027. So that's what this is doing. Okay, that's what this button is doing. It's turning the number over, and every number can be written as a fraction over 1. Okay, right. So, any rate. So what I've got here, all right, and I chose resistors, like I said here, recommend resistors with a brown third band. That puts them in the 100 ranges, not the thousands, and that's going to give us a slightly higher amperage, because higher amperages are usually more reasonable. Blue and gray, blue, black, brown, red, orange, yellow, green, blue. That's 6. So this is 680. This is a million here. So this is 1. Here, let me do this. Make it a little easier to see. This is going to be 1 million ohms. That's a mega ohm. So obviously very low current there. Okay, so that's 1 mega ohm. All right. I always have to do this. For some reason, the upper numbers I have trouble with. So it's black is 0. So it's black, brown, red, orange, yellow, green, blue. Blue is 6. I know gray is 8. So this is 680 here. That's a little higher than we're going to see in real life. Orange and orange is 3 and 3, so this is 330. That's getting closer to stuff we're going to see. Most of the stuff we work on is less than 300, 400 ohms, really less. Brown, green, brown. Green is 5, so it's black, brown, red, orange, yellow, green is 5. Okay, so brown, green, brown, that's 150. That's getting much closer to what we're going to see. And then brown, gray, brown is going to be 180. All right. So what I've done here is I've set this up, and I suggest you do this a couple of 3 or 4 times, and then practice putting series in, and I mean practice till you just understand it. All right. So this circuit is open here, so I'm isolated here. And if I read anywhere from here to here, which is the same thing as reading here to here to here to here to here to here, I guess maybe I'll use these because that's what I'm going to be doing, huh? Yep. So if I read from here to here, or 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 here to here, here to here, if I read at any of those points, what I'm expecting, okay, is I'm expecting the answer to be the same. And the reason I'm expecting the answer to be the same is because these are all electrically the same point, and this is one system. So the battery will be seeing one resistance for the whole system. But each resistor will carry its own current. So the current flow through this one, which is 1 million ohms, is going to be really, really, really low. This one's going to be the highest at 150. Then the 180, then the 330, then the 680, and so forth. But if I read resistance here, I read about 58, 55, 58 ohms. Okay? So how would I do this on the calculator. And I'm going to zoom in. I hate zooming in, but I'm going to zoom in because I have to then zoom out. And I have to reset the focus and stuff. My dog is staring at me. What do you need? What do you want to do? Do you want to go outside? What are you going to do? What are you going to do? Hey, Nike. What do you want to do? What do you want to do? You want to go outside? You want to go outside? What? We going to go outside? Okay. I'll be back in a minute, guys. I got to go outside with the dog. Let's go. Let's go. Come on. Come on. Come on. Come on. Come on. Come on. All right. I'm coming. I'm coming. Okay. I'm coming. I'm coming. I'm coming. I'm coming. Where am I? Hey. Here I come. Here I come. Here I come. Here I come. What? What are we doing? What are we doing? Okay. Come on. Kids named him Nike. Pretty cool dog. Not too bad. I'm not that much of a dog person, but as dogs go, he's pretty cool. Okay, so before I left, I demonstrated that I can read the resistance. And by the way, polarity doesn't typically matter, but more and more systems have diodes in them, so yeah, there becomes an issue. So there's the 58. I'll prove it. 58, doesn't matter where you do it because this is all one system. Now, those of you who deal with multiplexing, if there were two 120s, I'd read 60, and this is what's happening. So this would be the multiplex wires, blue and green or whatever they are, and then these would be the two resistors, and when you read from here to here, you'd read the 120. Now, we're obviously reading 168, but that's okay. So here's the thing. Let me do the math. Okay, so it's a teeter-totter, right? Okay, so the teeter-totter is that if the voltage, wrong. If the resistance goes down here, then the amperage goes up. Okay, well, you don't make the amperage go up to make the resistance go down. You make the resistance go down to make the amperage go up because volts and ohms make amps. If the resistance goes down here, then the amperage goes up. Okay, well, you don't make the amperage go up to make the resistance go down. You make the resistance go down to make the amperage go up because volts and ohms make amps. Okay, volts and ohms make amps. So the way you would say it is, well, if my amperage is increasing, then it's because my resistance is decreasing. Okay, don't get those confused. You must understand the difference. Okay, voltage and resistance make current do things. If current changes, it's because one of the other two things changed. Okay? You don't make amperage change something else. Amperage changed because of something else. Big, huge difference. Okay? Lower and lower and lower. So let's see if we can make the 58 work. Okay? And we know it was 58 here. I'm thinking I want to solder these in, but I'm not. Okay. So and by the way, you have to use volts, ohms, and amps. You can't use milliamps. Okay. And you can't use millivolts. It has to be volts, ohms, and amps. You have to convert it. Okay. 1, 2, 3, 4, 5, 6, a million. 1 over x. See? And that's 1 millionth. That's easy. Plus, just start at the top, 680 inverse plus 330 inverse plus 150 inverse plus 180 inverse plus. Now, this is the total resistance flipped over. So we have to flip it over again. And when we flip it over again, I hope we get something close to 58. We get 59.8. Okay, so that's pretty close. And let me put these here so I can zoom in on them. Okay, so now when I read the resistance, and this is the number we calculated using the pure numbers off the, and there's the 58.5, it's off by about an ohm, which is not bad. I mean, that's pretty good for what it is. Okay, so that is how you combine them. Okay, a couple of quick points here. First of all, I said a minute ago that no matter where I read on the left and the right, because everything is the same point, I'm going to get the same number. So as you can see, I can go anywhere I want, and I'm going to get the 58. I go here, I get the 58. I go here, I get the 58. Okay. This is also important to understand because if these two points here are the same electrical point as here, and these points here are the same electrical point as here, then the voltage here has to be the same as the voltage here, which has to be the same as the voltage here, and the same as the voltage here, and the same as the voltage here. And this is ground, so this is ground, this is ground, this is ground, and everything over here is ground, which means everything on this side is 12 and everything on this side is 0. Well, what that explains is what you're taught, that the voltage drops across the resistors are the same because the voltage coming in has to all go away and the voltage coming out has to be 0. So the reason for that sort of explanation is, I mean, it's just obvious, right? The pressure here is 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 the pressure here, pressure here, pressure here. This pressure is the same pressure. This pressure here is the same pressure. So if we have to drop 12, we drop 12. We drop 12, we drop 12. Doesn't matter the size of the resistance. The resistance has to use it all up. But what changes is the current flow. Okay? So this is important to understand. Very important to understand. The voltage is the pressure that pushes the current. The resistor is the obstruction which slows down the current. But Kirchhoff's law says whatever's coming in has to go away. So I'm going to see the same voltage here to here, here to here, here. These are all going to have the same voltage drops. Amperage is volts over ohms. Well, I know that this is going to be a 12.25 volt drop. So there's my voltage. And I just divide by the resistance, volts over ohms. And this is going to be a very, very small number. So 12.25 divided by 1, 2, 3, 4, 5, 6 equals 0.0000122. I don't even think we're going to be able to read that. 0.000122. I don't even think we're going to be able to read that. Amps. Now 680. So 12.25 divided by 680. That's going to be a much higher number because 680 is obviously a bigger hole. Be about 0.018. So that's going to be about 18 milliamps. So I'm going to just write it as 18 milliamps. Okay. Now 330 is about half of that. So this is going to be about 36 because the hole is twice as big. So I'm expecting 12.25 divided by 330 is about 370. So it's going to be about 37 milliamps. Okay. The 150, 2.25 divided by 150, volts over ohms equals amps, volts over ohms equals amps, volts over ohms equals amps. It's 81 or 82 milliamps. And finally, 12.25 divided by 180, which is slightly higher than this, so I expect this number to be a little lower, equals 68. Yeah, about 68. So it's 68 milliamps. Okay. All right. So I will zoom back out, and then we will actually turn this on and see what our total amperage is. And in seeing our total amperage, we will then calculate that as 12.25 volts divided by, we had 58 ohms. So I'm expecting about 0.211 amps total through the whole system.